Hello friends, so far we have been discussing about the mechanical behavior of a specific category of materials called metals and alloys. Now when we want to have, we saw that when we want to have a meaningful discussion about a mechanical behavior of any materials, we need to talk about two distinct components. So one is the mechanical condition that we impose, and the other is the response offered by the material to the imposed mechanical condition. Now the reason we have restricted our discussion thus far or even further is that the metals and alloy as a category of material, they offer a response to a given mechanical condition that can be discussed in a generalized way. Without getting into what specific metal or alloy we are dealing with, this category of materials, that is metals and alloys, they offer a response that can be discussed in a generalized way, and that is why we have began our discussion of mechanical behavior of materials from the metals and alloys. Now we saw that an elegant way, an understandable way of describing the mechanical behavior of material is using a graphical representation that comprises of two distinct axes. One, along the x-axis we consider the response offered by the material, and along the y-axis we consider the mechanical condition that we impose on the given material. Now we saw that this form of describing the mechanical behavior of materials, particularly when we consider metals and alloys and we describe the mechanical behavior of metals and alloy using this form of graphical illustration, the behavior that is offered by the metals and alloys can be schematically represented by a single curve. So metals and alloy, the behavior that is offered by it can be schematically represented by a single curve, and this curve comprises of different sections, and largely this can be these all different sections can be categorized into two: a linear section and a non-linear section. So what essentially we are doing is we are separating metals and alloys, studying the mechanical behavior of it, we imposing a mechanical condition, studying its response, and we are plotting it in this using this coordinate system, and we observe that all the behavior of all the metals and alloys can be represented schematically using this curve. Now the linear section, because of the nature of the behavior that occurs in this linear section, we refer to this section as the elastic section. So within this region, within the linear region, the metals and alloy, they exhibit the elastic behavior. Now when we talk about this plot here, the mechanical condition and the response offered by the material, we have been discussing about this plot for at least 3 lectures now. We have considered a macroscopic view of it, we have considered a microscopic or rather an atomistic view of it. We were able to relate, or we were able to arrive at the property that describes the elastic behavior, the property, a parameter that discusses or that quantifies the slope of the line along the in the linear section of the curve. We were able to arrive at the parameter of that specific parameter from an atomistic perspective. So all these discussion we have considered, or all these discussion we made in our previous lectures. Now despite all these different perspectives that we have rendered, be it macroscopic or be it atomistic perspective, these discussions were they were built on certain assumptions. So these discussions are rather limited. So what are the restrictions that are associated with this particular representation is what we will be considering in this lecture. So one specific limitation or the restriction that we have is that the mechanical condition that we impose on the material. This representation here, we have deemed it to be, or we have so far been considering it to be, the product of a specific form of a loading condition. So the mechanical condition we represented or we include in this description, it can be either in the form of load or it can be also stress. The same goes for the response, it can be the elongation or the strain. So despite these different modes of representing the mechanical condition and response, what we have assumed is, so what is the implicit assumptions that we have made while plotting or while considering this particular behavior of metals and alloy is, we have assumed to impose a uni-axial tensile loading. So supposing if we consider a simplistic sample like this, what we have assumed is we are imposing a uni-axial tensile loading along the longitudinal direction. So the restriction, the first restriction or the first another assumption we make while we are discussing the mechanical behavior in this context of the load elongation curve or the stress strain curve is that we are imposing a uni-axial tensile loading. And the other restriction or the assumption is we have so far been considering the response of the material exclusively in the form of elongation. So when we want to describe the response offered by the material, so far the discussion is restricted to elongation. So the elongation, which is the only way we have been discussing the response of the material, is nothing but the difference between the change in the or the length that is brought about by a given loading condition and the initial length. So when we are discussing the mechanical behavior that is offered by metals and alloys using this graphical illustration, we are making two assumptions. One is the mechanical condition that we impose is uni-axial tensile loading, and the response offered by the material is only along the longitudinal direction. So we are discussing response exclusively in terms of the change in the longitudinal dimension of the material alone. So we have not expanded or extended beyond these restrictions or these assumptions. So of course, in response to the mechanical condition, in response to the uni-axial tensile loading that is imposed along the longitudinal direction, there is a characteristic change in the longitudinal dimension of the material. However, we need to understand that that is not the only response that we observe. The purpose of this lecture, so what essentially we will be discussing in this lecture is we will be attempting to relax these two assumptions that we have made thus far. So we have made one assumption along the mechanical condition and the other assumption along the response. So mechanical condition, we have thus far been considering just uni-axial tensile loading alone, and in the response we have always been restricting ourselves to the elongation, the response of the material along the direction of the loading or along the length of the sample. So what we have ignored is we have ignored to see if there is any other response that accompanies the change in the dimension of the material along the length scale. So what essentially happens when you impose an uni-axial tensile loading for a metal or an alloy? What essentially happens is this change in the longitudinal dimension of the sample is accompanied by the change in the dimension along the perpendicular direction. So in order to make this discussion more understandable, so more comprehensive, let us begin by describing the different axes. So this axis along the length we can refer, or we have been referring it as longitudinal axis. So this axis is the longitudinal axis. So there is an axis that is perpendicular to the longitudinal axis, that is the lateral axis. So there is an axis that is perpendicular to the longitudinal axis. So this is the longitudinal axis, and we have an axis that is perpendicular to the longitudinal axis, that is the lateral axis, which we can refer to as the lateral axis. So we have two axes, longitudinal and lateral. Now so far the description of our response has been confined to the change in the dimension along the longitudinal axis. However, when we consider the response of metals and alloy, in addition to the change in the dimension along the longitudinal axis, there is also a change in the dimension along the lateral axis. So what we observe is, as the dimension of the sample extends along the longitudinal direction, so there is also a change along the dimension in the lateral direction. So this is how the response of the material ideally would be. So in addition to the change in the dimension along the longitudinal direction, along the length of the sample, there is also the change in the dimension along the lateral direction. So if you consider the longitudinal direction as x and the lateral direction as y, so if you consider an axis such as this, in addition to a change in the dimension along the longitudinal direction, there is also a change in the dimension along the lateral direction. So the change in the dimension along the x-axis is accompanied by a change in the dimension along the y-axis. So what we observe in most cases is that often as the dimension of the material increases along one direction, in the other direction the dimension decreases. So generally what we observe is, in general cases, what we observe is the change in the dimension, the response along the longitudinal direction is generally opposite to the response in the lateral direction. So this is what we generally observe. So there are two aspects we need to consider, that is, in metals and alloys, a longitudinal change is accompanied by the lateral change. However, the direction, the way in which the longitudinal change occurs, so in this case we have expansion or increase in the longitudinal dimension, is opposite to what we observe in most cases, is opposite to what we observe in the lateral direction. That is, there will be a shrinkage, a decrease in the dimension along the lateral direction. Now the question is, why does this happen? So what is the need for this, or what is what propels or what governs this specific behavior that we observe in metals and alloys? Now, in order to understand that, let us go back to our understanding of how the atoms are arranged in the metals. Now, while we've discussed about the failure of the metals and alloys, we saw that failure is nothing but the breakage of bonds between the atoms that constitute a metal or an alloy. So when you consider the arrangement of atoms in the metals and alloys, a simplistic case, because in metals and alloys the characteristic features is that the metals and the atoms that constitute these materials are periodically arranged. So a simplistic representation can be of this form. We saw that while discussing about the failure of the materials, the breakage of bonds that connects these two atoms is nothing but it ultimately leads to the failure of the entire component. Now let us render the same discussion here. Let us consider, or let us try to address, or let us try to comprehend this particular behavior, this typical behavior wherein the change in the longitudinal dimension is accompanied by the change in the lateral dimension using the same perspective. We will start with the arrangement of the atoms and the different bonds that connects these atoms. Now while discussing the failure of the material for tensile loading, we considered the bonds between the atoms of this sort. So since we are largely focusing on metals and alloys, so there exists a metallic bond between these atoms. Now, given the behavior, the mechanical behavior of materials to an imposed mechanical condition, so far we have been restricting ourselves to uni-axial tensile loading. Given the characteristic behavior of metals and alloys, it is rather reasonable for us to treat this bond as springs, because so it is possible for us, or reasonable for us, to treat these bonds that exist between the atoms in a metal or an alloy as springs. So meaning, when we impose a uni-axial tensile loading up to certain limit, these bonds act as springs, meaning they go beyond their position, they allow the atoms to go beyond their positions, so they allow the atoms to move here and here, so they allow them to move here and here, and once you remove the load, the atoms, they get back to their original position, meaning they resume their original location, and therefore we can assume, at least for within the elastic limit, the bonds that exist between the atoms can be treated as springs. Now, while discussing the failure of the material, these are the only bonds that we considered. However, in addition to these spring-like bonds that exist between the metal atoms, there is also the bonds that connect these two atoms here. Spring-like bonds that connects these atoms here. So not only in the longitudinal direction we have bonds, we also have bonds along the lateral direction. So for our intents and purposes, since our focus was on the failure of materials, along the loading direction, or for the uni-axial tensile loading in the previous lectures we considered only the bonds along this particular direction. We have not considered the bonds along the lateral direction. However, now that we want to extend our focus to considering the behavior of materials along the lateral direction, we need to consider the bonds along the lateral direction. And when we do so, now it is possible for us to understand that when you impose a uni-axial tensile loading, when there is an extension, where there is a shift in the position of the atoms from their original position to these positions here, since we have established a continuum through the bond, since we have established a continuum, there is a change along the lateral direction also in addition to the longitudinal direction. So what the reason behind this particular behavior, the change in the lateral dimension, or in addition to the longitudinal dimension when you impose a uni-axial tensile loading, stems from the continuum that is established between the atoms that comprises of metals and alloys. So in metals and alloys, you have regular arrangement of the atoms, and these regular arrangement of the atoms, they establish a continuum through these bonds. Through these spring-like bonds, they establish a continuum. So therefore, when the atoms tend to move in a specific direction, when they tend to move along or move their positions in a specific direction, it is also they also tend to pull the other surrounding atoms in order to accommodate this movement, in order to ensure that this continuity is maintained. So there is no breakage of bonds. These atoms, they tend to accommodate, or they tend to move in such a way that this continuity is maintained. There is no breakage of bond. This propagation or this movement of atoms in response to uni-axial tensile loading, to ensure the continuity that is established in the system, ultimately leads us to the effect that we see. So what essentially we have is, we have a continuous system, and in that continuous system we have atoms that are regularly arranged, and these atoms are not suspended in the air, they are connected with one another. Now when you impose a uni-axial tensile loading, they exhibit a response for the uni-axial, so they exhibit a response, and this response need to ensure that this continuity is sustained despite the change in the position of the atoms. So when you want to have a response that despite the change in the position of the atom, the continuity is maintained, the periodic arrangement is maintained, you have a change in the lateral dimension in addition to the change in the longitudinal dimension. So therefore, in most metals and alloys, we observe this change in the lateral dimension along with the change in the longitudinal dimension. Since in metals, the atoms are regularly arranged, and the continuum is established by the bonds that exist between these regularly arranged atoms. When there is a longitudinal dimension, this regular arrangement and also the continuum needs to be maintained, and it is only possible when your longitudinal change in the dimension is accompanied by the lateral change in the dimension. And that is the reason why when the atoms move their position along this direction, they get closer in order to establish, in order to sustain the regular arrangement and also the continuity, the continuum in the system. Now, having discussed or having introduced that the longitudinal change in the dimension is accompanied by the lateral change, and having seen why this occurs, now it becomes rather critical for us to describe these different change in the dimension. So we have already described the change in the response along the longitudinal dimension. So the change in the response along the longitudinal dimension, we refer to it as the elongation dl, which is nothing but the difference in the length when compared to the original length. So we have a change in the length once you impose the loading, and we compare it, we take the difference between this the increased length to that of the original length, and that yields us the elongation. Now when we want to consider the strain, the corresponding strain along the longitudinal direction, what we do is we take the ratio of the elongation, the change in the dimension along the longitudinal direction, to that of the original length. So this is something that we are familiar with, we have looked into. So this lastly or principally it talks about the response of the material in the longitudinal dimension or in the longitudinal direction. Now we can offer a similar description for the change in the dimension along the longitudinal or the lateral direction. So for that, let us consider the width of the sample to be B0, the original width of the sample to be B0. Now in that case, the corresponding change in the dimension along the lateral direction can be expressed as dB, which is nothing but the change in the lateral direction in response to the load minus the original dimension. So in case of elongation, we have taken the difference between the length in response to the load and subtracted it or taken its difference with respect to the original dimension. The same we are doing it for the lateral direction. We assume that along the lateral direction, the size of the dimension of the sample is B0, and we are considering the response along the lateral direction as B minus B0. B is the change in the lateral dimension in response to the loading. Now we can also describe in the similar way the elongation along the lateral direction, which is nothing but the change in the dimension along the lateral direction with respect to, we can just take the ratio of the change in the dimension along the lateral direction to that of the original dimension along the lateral direction. So we have used the same format or the same approach to describe the change in the dimension along the lateral direction and also the strain along the lateral direction. So what we have is, for just a uni-axial tensile loading, we have combination of two strains. One is the longitudinal strain and the other is the lateral strain, and the way we describe these two strains are the same. We are taking the ratio of change in the corresponding or change in the dimension in the corresponding direction to the original dimension in that particular direction. So in the elongation case, it is the change in the length to the original length. In case of lateral strain, it is the ratio of change in the breadth to that of the original breadth or the width. Now we have considered the complete, or we have extended our assumption, and we have now an additional dimension to the strain that we observe, the response that we observe for uni-axial tensile loading. So far the uni-axial tensile loading has largely been confined to the change in the dimension along the longitudinal direction, and to that we have now used, or we have now introduced a parameter to describe the change in the dimension along the lateral direction. So we now have seen, for just one form of loading condition, there are two different strains that are possible. Now what we need is, we need to find a way to describe both these strains in using a single parameter. Let me repeat, both these strains, even though we have distinguished longitudinal strain and lateral strain, or we have expressed it separately, both these strains are the response of a single form of loading. We are not separately imposing any different loading condition to bring about longitudinal strain separately or lateral strain separately. It is in response to a single form of loading, a single form of uni-axial loading, we get both these longitudinal and lateral strain. So since both these emerge from a single form of loading, what we essentially need is, we need a parameter which can comprehensively discuss both the longitudinal strain and the lateral strain. So one easiest way of arriving at such a parameter that discusses about, or that talks about, that quantifies both the lateral strain and the longitudinal strain is just by taking the ratio of the lateral strain and the longitudinal strain. So what we essentially want to do is, since both these responses, since they stem from a single mechanical condition, we want to have a parameter that talks about both these different forms of strains. So what the simplest way, we have taken the simplest route, that is just we are taking the ratio of the lateral strain to that of the longitudinal strain. And now, before we give a name to this ratio, or we attribute a name to this parameter, let us consider one critical aspect of these different forms of strain. Now when we have already seen, or if you reconsider the terms that are associated with the longitudinal strains, so it is the elongation to that of the original length. So it is L, the length of the material, the length of the sample to the imposed loading condition minus the original length, and the ratio is taken with respect to the original length. Now since we are imposing a uni-axial tensile loading, or generally the length for a given loading condition, uni-axial tensile loading condition, the length is greater than the original length. For any load that you are imposing, uni-axial tensile load that is you are imposing on the sample, the length, the responsive change in the length is greater than the original length. So therefore, this particular term, that is longitudinal strain, is largely positive. It is largely greater than 0 and it is positive. However, on the other hand, if you consider in a similar way, if you consider the lateral strain, what we have is, we have the similar to the description of the longitudinal strain, the lateral strain is, first the numerator we consider the difference between the dimension that we have in response to the uni-axial tensile loading and the original lateral dimension, and the ratio is taken with respect to the lateral dimension. So the description is the same. However, there is a key difference, that is, when you impose or when you consider the lateral strain alone, what we observe is this lateral strain that accompany the longitudinal strain. In this case here, what we see is the dimension of the sample along the lateral direction, it tends to decrease when compared to that of its original dimension. So here in the original instance, we have the lateral dimension to be B0, but after imposing the loading, what we end up having is B, and this B is less than B0. So ultimately, as it stands, since given the nature of the change that we see along in the lateral direction, since B, the dimension along the lateral direction once you impose the load, is less than the initial dimension, as it stands, this lateral strain assumes a negative value. It's less than 0 and it assumes a negative value. So therefore, as it stands, this ratio 2 assumes a negative value. However, we need to understand that. So we need to bring about a specific aspect of describing this ratio here. That is, when you consider the change in the lateral dimension, when you consider the change in B, this same change can be brought about by introducing a compressive load. So when you impose a compressive load along the lateral direction, it will be possible for us to bring about the same change in the dimension as we see now. So what we essentially have is, we see that along the lateral direction, because of the uni-axial tensile loading, there is a decrease in the size. So if there is a decrease in size decrease in dimension along the lateral direction because of the uni-axial tensile loading. However, it is also possible for us to bring about the same change in the dimension when we impose the uni-axial, or when we impose a compressive load along this direction here. When you impose a compressive load along the lateral direction, we will be able to bring about or establish the same response. So that means this response, this change in the dimension along the lateral direction, this change in the dimension from B0 to B along the lateral direction can be assumed to be brought about by a compressive stress or a compressive load. So let me repeat, we observe a change in the dimension along the lateral direction that is brought about by uni-axial tensile loading, and it is possible for us to see that the same change in the dimension can be brought about by a compressive load along the lateral direction. So then we can also assume that the change in the dimension is brought about by a compressive load that is introduced in response along with the uni-axial tensile loading. So therefore, this assumption allows us to introduce a negative sign here, because since it is possible for us to reasonably state that this change in the dimension along the lateral direction can be brought about, or in this case is brought about by a negative, or rather a compressive load along the lateral direction, and since by convention a compressive load is accompanied by the negative sign, it is possible for us, or it is reasonable for us to introduce a negative sign here. So once you introduce a negative sign here, what essentially happens is the numerator it turns positive, and since the denominator is already positive, the entire ratio becomes positive, and this ratio is what we refer to as the Poisson's ratio. So this ratio is referred to as the Poisson's ratio. Here the key aspect we need to understand. So there are a couple of key aspects we need to understand. One is when you impose a uni-axial tensile loading, there is, in addition to the change in the dimension along the direction of loading, there is also a change in the dimension in the direction that is perpendicular to the direction of loading. So this direction we call it as the lateral direction. Now we saw that in most cases the change in the dimension along the lateral direction is opposite to the change in the dimension along the longitudinal direction, meaning along the longitudinal direction the dimension increases, whereas in the lateral direction the dimension decreases. Now when we express the strain, the longitudinal and lateral strain as it is, the lateral strain would assume a negative value and the longitudinal strain would assume a positive value. But when you consider the nature of the load that brings about the change in the dimension along the lateral direction, when you consider the nature of the load that brings about the change along the lateral direction, we can assume it to be a compressive load. So therefore when you assume it to be a compressive load, we need to by convention bring about a negative sign here, and when you bring a negative sign here, then both numerator and denominator is always positive, so it has been positive, and the numerator now also becomes positive because of the negative sign that is brought in by the convention. So therefore ultimately what we end up having is a positive ratio, and this positive ratio is called as Poisson's ratio. So when you see a metal or an alloy that exhibits a lateral shrinkage when you impose a uni-axial tensile loading, so you impose a uni-axial tensile loading and there is an increase in length, and in addition to the increase in length you observe there is a decrease in the lateral dimension, then that material exhibits a positive Poisson's effect. So, and the ratio between the negative of the lateral strain or the longitudinal strain is referred to as the Poisson's ratio. Now what we have essentially done is, using the Poisson's ratio, we have introduced a parameter that can discuss or that can describe both the longitudinal strain and also the lateral strain. So initially when we are discussing about this particular plot here, we have restricted ourselves to the longitudinal response alone. Now we have a parameter that encompasses both lateral strain and also the longitudinal strain. So we began with two specific restrictions. One restriction is associated with the response that we consider, that is we have been focusing largely on the longitudinal response alone, so we wanted to relax that assumption. Now we have considered the lateral change in the lateral dimension, we have considered the lateral strain, and now we have introduced a parameter that can discuss or that can describe both lateral strain and the longitudinal strain. Now the second relaxation that we need to make is, how would be the response of a given material when instead of uni-axial tensile loading we introduce a bi-axial? What would be the response of the material when we impose a bi-axial tensile loading? So far we have been considering or restricting ourselves to uni-axial tensile loading. Now we want to extend our discussion to the bi-axial tensile loading. So uni-axial tensile loading, we described it as tensile load that has been imposed in the longitudinal along the length of the sample that we have. Now we want to have a biaxial tensile loading, so there is another load that is imposed in the opposite direction. So what we have is, we have a tensile load that is imposed along the longitudinal direction, a specific longitudinal direction, and there is also, in addition to that, we have a load that is imposed on a specific direction along the perpendicular to the longitudinal direction. So we have now a longitudinal load, we have a longitudinal load, and in addition to that we have a lateral load. So we are moving away from the straightforward consideration of just the uni-axial tensile loading to biaxial tensile loading. So biaxial tensile loading, what it essentially means that we are imposing load along the longitudinal direction and also along the lateral direction. So once we are able to quantify this load, by considering the corresponding dimension, we will be able to quantify the longitudinal stress and also the lateral stress. Now, under the biaxial condition, we want to discuss describe what is the response offered by the material. So initially we just focused on the response offered by the material along the loading direction alone. So when we consider this depiction here, we considered the response offered by the material along the loading direction alone, so along the longitudinal direction alone. However, using the Poisson's ratio, we also in the context of the Poisson's ratio, we also introduce the strain along the direction perpendicular to the loading direction. So in case of uni-axial tensile loading, we had two strains, that is lateral strain, that is in the direction perpendicular to the loading direction, and longitudinal strain, that is along the direction of the loading condition. Now this is for uni-axial case. Now we want to consider what are the response, or what is the response of the material for biaxial tensile loading. In order to do that, let us begin by just expressing what are the different forms of strain that we can expect. So let us, in order to do that, we will first consider, or we will set up a framework, a coordinate system. So let this direction be x and this direction be y. Now before quantifying the response of the material, let us just refer, or let's just indicate what are the different strains that we could expect for a biaxial tensile loading. So we have now loading in two directions. So along the loading direction, we can expect a response. Along the loading direction, we can expect a response. Along the loading direction, it means we can expect a strain. So therefore, there will be a strain along the x-axis, and also there will be a strain along the y-axis, and these two strains are in response to the load along the x-axis and the load along the y-axis. So we have biaxial loading condition. So there is stress along the x-axis and a stress along the y-axis. So in response to the stress along the x-axis, along the same axis, you have this particular strain. So in response to the stress along the x-axis, you have this particular strain, and in the stress along the y-axis, you have this particular strain. Now, in addition to the response along the same direction, we also have the response along the perpendicular direction as well, meaning for the stress along the x-axis, we also have a change in the dimension along the y-axis, like we have seen in the uni-axial tensile loading. For a stress along the x-axis, we will also have a response that is introduced along the lateral direction, that is the y-axis. So therefore, having such a representation will not be sufficient. So we need to have an extended way of representing the responses. So a general way, also one way we can represent it by considering two instead of one, by considering two subscripts. So what essentially we are trying to do is, we are trying to just describe the different strains that are possible when we are imposing biaxial tensile loading. So for a given loading, there are two responses, one response along the loading direction and the other response is the perpendicular direction. For a given load, there are two responses along the loading direction, perpendicular to the loading direction. So for sigma x, there will be two responses or strains, and for sigma y, there will be two responses similarly or strains. So what it means is that For sigma x, there will be a strain along the loading direction and also along the perpendicular direction. So in order to describe it, we need appropriate parameters, and that appropriate parameter can be expressed using two subscripts. So the first subscript here, it indicates the strain direction. So in both these cases, the first subscript, it indicates the strain direction. However, the second subscript, it indicates the load or the stress direction that brings about the strain. So since there are two responses associated with each strain, so each load, so in case of biaxial tensile loading, we have load acting in two directions. For each of these loads, we have two responses associated with it, and therefore we need to have a specific form of representation. So generally what we do is we introduce two subscripts. The first subscript, it indicates the strain direction, and the second subscript, it indicates the loading direction. So this response here, that is epsilon xx, what it indicates is this response is along the x-axis and it is brought about by the load along the same direction, that is sigma x. And in the same way is epsilon yy, it indicates the response along the y direction and it is brought about by the load along the same direction. Now in addition to these two responses, so we can refer to these as direct responses. So these two responses are direct responses because they occur along the loading direction. You impose sigma x along the longitudinal direction, consequently there is a change in the length along the same direction, and that is represented by epsilon xx. In the same way, you are imposing a load along the y-axis. In response to it, there is in response to this load along the y direction, there is a corresponding strain, and that you have represented by yy. The first subscript is the direction of the strain, the direction of how the strain occurs, and the second subscript is the direction of the loop. Now there is also an indirect response that is offered by the material for biaxial tensile loading. So this indirect response comes from the Poisson's effect. So the Poisson's effect, it brings an indirect response. So what we mean by indirect responses, for the sigma x, in addition to the change in the dimension or along the x-axis, there is also a change in the dimension along the y-axis. Let me repeat, for sigma x, in addition to the direct response along the x-axis, there is also, due to the Poisson's effect, a response along the y-axis. The same goes for sigma y. In addition to the direct response along the y-axis, we also have, so in addition to sigma xx and sigma yy, we will also have two combinations of strains that are represented by sigma xy and sigma yx. So ultimately we have four different responses that is offered during biaxial tensile loading. So two of them are direct responses, two of them are indirect responses that are rendered by the Poisson's effect. So the direct responses, they have same subscript, whereas the indirect responses, they have different subscripts. So we have discussed these response in terms of strains. So the epsilon has two subscripts associated with it. When the subscripts are the same, they are the direct response, meaning they occur along the loading direction. However, when the subscripts are different, they are indirect effect, they are occurring in the direction that are perpendicular to the loading direction because of the Poisson's effect. So ultimately, what happens when we impose a biaxial tensile loading is the amount of response that we observe increases. Initially, for uni-axial tensile loading, we just saw one lateral strain and one longitudinal strain. For biaxial tensile loading, we have four forms of strains, two lateral and two longitudinal. These two longitudinal strains, they have similar subscripts. So, meaning the strain along the loading direction, they have similar subscript. The strain along the opposite direction, they have dissimilar subscript. So when you increase or when you make the loading or the mechanical condition that you impose a bit complex, what you essentially end up having is you increase the complexity that associated with the response that we observe. We increase the number of strains that we observe. So we will attempt to rather unify all these different strains in the upcoming lecture. So the principal takeaway of this consideration of biaxial tensile loading is when you increase the loading, or when you rather convolute the mechanical condition that we impose on a material, when we shift from uni-axial tensile loading to biaxial tensile loading, the response that we observe correspondingly varies. We will try to unify these different responses in the subsequent lecture. Goodbye.